So one more time, we're going to take a look at the motion of a charged particle in a uniform magnetic field. And this is why we're going to look at it. We're going to look at it because you guys have noticed, first of all, we just did it very kind of qualitatively with the right-hand rule. And we said the force will always be inward, whatever inward happens to be. Second thing we said was, then we looked at it in more detail and said, okay, now let's look at an arbitrary orientation. And we saw that not only is the force always inward, but that results, as it logically makes sense, it will, since the velocity is not magnitude, the velocity is not changing, that it results in circular motion. And now you might ask, well, if it's circular motion, why don't we use some kind of circular coordinates? So polar coordinates, or since this is three-dimensional, it will be cylindrical coordinates would be the appropriate symmetry to choose. So that's what we're going to do. And we will see that indeed it can make our lives a little bit simpler. Okay, so let's go ahead and just define our coordinate system a little bit here. Once again, we have x, y, and z. Our b, as you'll remember, is into the board. Like I said, I'm not sure if when this is flipped that might look backwards, but it works consistently. Okay, so there's our b. And now we have, let's go ahead and start with our velocity just like that. So the question is, in these coordinates, how do we express this vector? What are the vector coordinates in this cylindrical coordinate system? Well, what we need here, we need three parameters. We need r, theta, and z, which is just the distance out of this plane. We don't have to mess with z right now, except that we know that b is in the direction of z. So our z hat vector is very easy. It's just going in this direction. But what about the other two vectors? Well, r is easy. R is my vector, so r hat is just a vector that goes in this direction, a unit vector. And theta hat is just a unit vector that goes in the theta direction. But what you guys will notice is that these directions are not constant. They're constant in terms of this coordinate system, but if you were actually looking at them, you would see that as opposed to Cartesian coordinates, where those are always the same, these are not always the same. They change. And so in other words, if I'm at this location right here, then my r hat is like that. And if I'm and my theta hat is like this. But now if I am at this location right here, now my r hat is like this, and my theta hat is like that. And you will notice that they've essentially traded places. This was theta hat up here, and here it's r hat. But it's the same direction. This was r hat here, and here it is theta hat, which is minus r hat, as you can see from that. Okay, so we just want to keep that in mind. So now, in terms of this, what is our initial velocity? Well, our initial velocity is just v equals v0 theta hat, right? There's no component in the r direction. We're going just in this direction. So we can, let me get rid of some of these definitions here. We can go ahead and do the exact same cross product that we did before. So what we will do, let's just go ahead and get rid of that for now. Our b, we know, is in the z hat direction. So what we have is, I'll go ahead and write that, b equals b0, and in the z hat, I'm going to go ahead and leave it at that. Okay, so now the question is, what is q v, oops, excuse me, don't want that yet, q v cross b. And it is just q, and then we're going to do the same thing we did before, but now we're going to do our determinant in the cylindrical coordinates. So, yeah, I'm just going to move this. Q, V, cross B. We're doing the cylindrical coordinates. So what do we have? We have r hat, theta hat, z hat. And what do we have for our vector components? Well, we have 0 in the r hat for velocity. We have a v0 in the theta hat, and we have 0 in z. Meanwhile, for b, what do we have? We have 0, 0, b, 0. And so this is just about as easy as this will ever get, because what is it? It's just the only non-zero term is b0, v0 in the r hat direction. And this now equals our force. Okay, so now here's the only tricky part with this one. We're going to do the exact same thing now we did before. What did we do before? We said we know that this is the force, and we know that Newton tells us F equals ma, which is mv dot, and we know that equals our force. And these are all vectors, of course. Okay, so we now know that our force, I'm going to go ahead and write that up here. Our force equals B0, V0, R hat. Okay. So I can get rid of not quite all this stuff. Okay. So now you'll recall that V0, we made a pretty reasonable argument that V0 could not change. So V0 is constant. So what the heck is V dot then? If V0 is not changing, what is changing? Well, what's changing, as we just looked at, is that theta hat is changing. And how do we figure out what that change is? Well, same way we figure out what, same way we account for any change of a variable that goes with time. We say, what is d theta hat d theta, and then what's d theta dt? Okay, well, what is d theta hat d theta? Be an interesting thing to look at. So, here's the question. Here's theta hat. And the question is, what happens as theta changes? As theta changes, what happens? So if I now go here, now I have a new theta hat. Now, the rigorous way to do this is to actually define this theta hat in terms of Cartesian coordinates. And if you do that, you will see that theta hat is, let's see if I can get this right here. Here's theta equals 0, so it is cosine theta in the y hat direction, and that's plus, and it is minus sine theta in the x hat direction. And if you do that, you can then figure out what this d theta hat d theta is just by doing this. But we're going to just look at it kind of qualitatively right now. And what we're going to do, so like I said, it's pretty darn straightforward. You guys can take this derivative, the derivative of this, with respect to theta, and see what you come up with. What you will find, however, is that this change from here to here is in this direction. So what is that? That is the minus r hat direction. So minus r hat theta dot is equal to, this is equal to theta hat dot. Okay? All right. So now we know what our velocity time derivative is. So let's go ahead and set that equation up once again, because all we're doing is this equation, F equals ma. So we have V0 minus V0, r hat theta dot, and that's just V, excuse me, I forgot the m. I'm going to just pop the m right over here. And this is going to equal, this is ma, and this is f, B0, V0, r hat. And you'll notice that we're actually working with the same component here. We now have we have the r hat equation that we have set up. So we are going to, what we really have here is magnitude V0 m theta dot equals B0 V0. Oops. This is not F. I forgot the Q. It's QV cross B. So there's a Q in here, and there's a Q in there. Okay, so what are we going to do? We're just going to divide both sides by V0 and get rid of those terms. And what do we have? What end up with? We end up with theta dot equals minus Q B0 over M. Now, question, does this look familiar from anything else? Yes, it's the exact same result we got from when we were using Cartesian coordinates. And now, because of that, all the rest of the discussion is exactly the same as it was before. So you can just what can I say? Well, I'm just going to leave it at that. So you can do this in Cartesian coordinates. You can go straight to Cartesian coordinates and do the exact same thing as you did before, because this is the exact same result as before. Or you can do this in cylindrical coordinates, where you will find that what we have is we have an object that's just moving around in a circle. Okay, I am going to leave it at that, and I think we're pretty much done with this topic of a moving charge in a uniform magnetic field.